Hello there, folks. Today we were talking about proving segment relationships. This is Geometry, Chapter 2, Section 7, and we are nearing the end. We have one more section after this. But today we want to talk about segment relationships and a couple of postulates that we have in this section. And so the first postulate is what we call the ruler postulate. And the ruler postulate states that the points on any line or line segment can be put into one-to-one correspondence with real numbers. Now that might sound very technical, but you've already used the ruler postulate in the past. In lesson 1-2, we measured segments with a ruler by matching the mark for 0 with one of the endpoints and then finding the number on the ruler that corresponded to the other endpoint. And that basically is how the ruler postulate works. It's more important for us to know what we can do with it as opposed to trying to get all technical with the definition. So basically it means that for every real number that we have, even like 1.3 and 0.79, that all of those numbers are also on the ruler. So it basically means that we can measure things. So we kind of line up the A with 0 and the B with the 3, and so because of that, we know that this segment is 3 units long. So that's just kind of what the ruler postulate is, but I wanted to make sure that you had it there. And then we also have what we call the segment addition postulate. And again, remember that postulates are things that we do not have to prove. They are kind of like common sense, if you will. It makes you don't have to prove it. It's pretty. It makes pretty direct that that it's going to be true. So anyway, our next little guy here is, if A, B, and C are collinear, and that is important, if A, B, and C were not collinear, I kind of want to give you an example of what would happen if A, B, and C were not collinear. So here's A to B, and then let's say that C's up there, okay? It says here that if A, B, and C are collinear, then point B is going to be between A and C if and only if the segment from A to B, the measurement of A to B, added to the measurement from B to C will equal the measurement from A to C. So I've kind of done in pink here what the segment of AB is, in green BC, and then the entire thing is AC. So basically what it's saying is that if you take a segment and cut it up into different parts, and if you add those parts together, it should equal the whole. And that is not the case when you have something that's not collinear. The distance from A to B added to the distance from B to C, and this would be AC. And in that case, when you add A, B, and B, C together, it's actually not the same as A to C. A to C actually ends up being a little bit shorter. So it's not true when you have points that are not collinear. So it is important that we only apply this when we know that the 3 points are collinear first. But otherwise, if that happens, if they are collinear, then basically it means that the two pieces of the segment can be added together to equal the whole. So we're going to now see what that means for us. So here we go. We have an example here. It says, prove that if CE is congruent to FE and ED is congruent to EG, then CD equals FG. So I kind of want to just make sure that with the proofs, I kind of go through all the steps with you. Remember that the given is always the hypothesis of an if-then statement. So we have an if and we have a then, and my hypothesis is this part. So that's basically what goes in the given. So I'm going to put CE is congruent to segment FE, and also that segment ED is congruent to segment EG. And then my conclusion over here is going to become what I'm being asked to prove, and that is that CD is congruent to FG. All right? And so then we can start the proof writing process over here. We have some a diagram over here. So basically what we're saying is that CE, which is right here, is congruent to FE. And we also, that ED, which is this guy, is congruent to EG. So I'm going to mark my diagram over there as well. So for my very first step, we always start with the given. So this will be no different. And for our very first step, we're going to put CE congruent to FE, but also we're going to put ED congruent to EG. And of course, our reason for that being given. All right, so the next question we need to ask ourselves is, what does it mean for CE, for segment CE to be congruent to segment FE? And that is that we can take this from a congruent statement to an equivalence statement. So now we can say that CE, remember no bar, is equal to FE, no bar. And also that ED with no bar is equal to EG, also no bar. So basically we're going to take from having the bars, the segment bar, and the congruent symbol to having no bar and an equal sign instead of the congruent symbol. And that's going to be for definition of congruence. That's what it means to be congruent. Definition of, I'm going to abbreviate here a little bit. Okay, and now is where it starts getting more interesting for us. We're now going to use the segment addition postulate, which we just talked about earlier. And we're going to say that CE plus ED is equal to CD. So all I'm saying here is that the distance, or the distance from C to E added to the distance from E to D will equal the distance from C to D. That's basically the segment addition postulate in a nutshell right there. Segment addition post, abbreviating here. Okay, and then we're going to use substitution for our next step, and I hope that you can follow along here. So I will show you, we're going to take steps 2 and 3, and we're going to use substitution. I know that CE is equal to FE, so instead of CE here, I'm going to put FE, okay? And then, instead of ED, I'm going to put EG. All right, so just so that we're clear, and I'm going to put over here substitution, which we said we could use subs as an abbreviation, and this is going to be steps 2 and 3, and this is helpful for you to write what steps you're using so that someone reading your proof will know what they're talking about. So I'm basically taking the information from step 2, which is that CE is equivalent to FE, and then in step 3, when it says CE, I'm replacing it with FE. That's substitution. I'm also taking the segment ED and replacing it with EG because, again, they're equivalent from step 2. So that's kind of what happened in step 4 there. So now we have that FE plus EG equals CD. And then we're going to do segment addition postulate again. This time, we're going to say that FE, which is this piece right here, FE, added to EG is equal to the entire segment, which is FG. And again, that's going to be segment addition, and I'll get out of the way here in a second, postulate. Okay? So FE plus EG equals FG. FE plus EG equals FG. And now, I'm going to use these two steps together because, as you can see here, we already said in step 4 that FE and EG were equal to CD. And now we're saying that FE and EG is equal to FG. So I can replace FE plus EG with CD instead. That's what it equals to. So now I say CD equals FG. Okay, in step 6. CD equals FG. And that's going to be substitution. And just like before, I'm going to put steps, in this case I was using steps 4 and 5. So I'll make a note of that. And then our last step, we kind of already have here, we want to prove that CD is congruent to FG. So we only have to do one more step. I don't know why I put 8 there. But we have one more step, and that is to take and put the bar back, put the congruent symbol back. So now CD is congruent to FG, and our reasoning there is because definition of congruence again. The definition of congruence is that when two segments are congruent, then their measures are equal. So there is my proof for this little guy, and using the segment addition postulate. So now we're going to have you try this guy. Now the good news is you don't have to do the whole proof by yourself. You need to copy this down and complete the proof. There's only like 5 question marks. You need to provide the reason for B. You need to provide the missing pieces for part C here. You need to provide the reason for D, and you need to provide step F in the proof. So it's mostly done for you. There's a couple of things that you need to fill in. All right, and then we're going to go to properties of segment congruence. We've already done these with equality, when things are equal, and they're very similar when you're talking about segment congruence. So there's a reflexive property, and what that means is that segment AB is congruent to itself, segment AB. The symmetric property of congruence says that if a segment AB is congruent to segment CD, then the reverse of that is true, that segment CD would be congruent to segment AB. And then the transitive property again is that if segment AB is congruent to segment CD, and in turn segment CD is congruent to segment EF, then we can kind of get rid of the middleman, in this case CD, and we can just say that segment AB is congruent to segment EF. So we're going to be using some of that in our next example, and it's kind of crazy. Now in the book, you will find this example, let me see here on page 146, and there's a nice little map diagram going on, but I only copied onto the board the part that was crucial, which is this part right here. Okay, and it is a bit wordy, so I kind of just want to walk you through it, and then we can fill in what we need to know here. It says the route for a charity fitness run is shown, and this is like the route. There's all kinds of streets and stuff this is like the corner of a town or something. So again, if you look at the book, you'll see the whole picture, but this is basically what it looks like. It says checkpoints X and Z, so here we are the midpoints. They're in the middle. Between what? Between the starting line, which is here, and checkpoint Y, which is here. So X is the midpoint of S and Y, okay? It also says that it's that Z is the midpoint, so Z is also a midpoint between checkpoint Y and the finish line, so Y and the finish line. So basically, X and Z are midpoints of their respective segments, okay? It says if checkpoint Y, here we are again, if checkpoint Y is the same distance from checkpoint X, so if checkpoint Y is the same distance, it's equivalent to both of those. It says again, if checkpoint Y is the same distance from checkpoints X and Z, and that's why I've marked it there, it says then prove that the route from checkpoint Z, so from Z to the finish line, is the same as the route from the starting line to X. So they want us to prove that this red portion is the same as the orange portion, provided that the blue portion is the same as this green portion. Okay, that's basically what they're asking us to do. So the first thing we have to do is come over here to the given, and what do we know? Again, it's very wordy, but what they did say was that X and Z were midpoints, okay? So we're going to write that up for X is the midpoint, okay, of SY. And SY, so here's S to Y. X is the midpoint. But also we know that Z is the midpoint of FY, or YF. I'll put YF here to stay consistent. Okay, so that's the first part that they told us, but they also said later on that checkpoint Y is the same distance from X and Z, which tells us that the distance between the two, so I'm going to keep it over here, XY equals ZY, or YZ. Again, it's not a congruence, it's saying that they're the same distance. And I'm talking about distance, you don't use the bar. So XY equals YZ or ZY. Okay? I'm going to stay consistent with the book and call this YZ. So now we have what was given, and then it's asking us to prove something. It's saying, provided all that information is true, it says, prove that the route from checkpoint Z to the finish line. So that would basically be ZF. They want me to prove that ZF is congruent. It says right here is congruent. So they want to know that ZF is congruent to the route from the starting line, which is S, to checkpoint X, so SX. That's what they want me to prove. All right? So now we're going to go into our proof, and that should be, once you have all that information down, it shouldn't be too complicated. But we are going to have to use the segment addition postulate. So here we go. We're going to start with, and I've color-coded everything over there. So the first thing that we know for our given here, okay, I don't know what's going on here. It's getting crazy. Okay, so we're going to rewrite our given. X is, I'm going to try to abbreviate here. I don't have that much space. X is midpoint of SY. Z is midpoint of YF. And I might have to erase a little bit of this here and come back and do that again because I'm running out of space. So I have X is the midpoint of SY, Z is the midpoint, I forgot my I, sorry. Z is the midpoint of YF, and then we also have that XY equals YZ. All that is given. Okay? So now in step 2, what does it mean to be the midpoint? Well, it means if X is the midpoint of S to Y, it means that SX, and I've color-coded it, so you can see there SX is congruent to XY. And XY is blue. Okay? I hope that makes sense. So I've kind of color-coded it on the diagram, I've color-coded it on the actual proof so you can kind of keep things straight. So SX is congruent to XY, but also we know that Z is the midpoint of YF. So that means that also YZ is congruent to ZF. And YZ is going to be green, so we're going to come over here. YZ is congruent to EF. Okay? Sorry, ZF, not EF. Wrong letter. Okay, ZF. And then we have to put our reasoning for that is the midpoint theorem that we learned in the last section. Midpoint theorem. Abbreviating there, okay? Midpoint theorem, okay? So now we're going to go to step 3. And in step 3, we can take and use some congruent statements here. We know from this piece right here, from step 1, that XY equals YZ, which means that segment XY, which is the blue part, segment XY is congruent to, where am I here? YZ, and YZ is the green part. Okay, so just want to make sure that you understand. Because X and Z are midpoints, we got step 2. And because XY equals YZ, we get step 3, which is that segment XY is congruent to segment YZ. So that's definition of congruence. Alrighty. And then we can go to step 4. And in step 4, we're going to use the transitive property of congruence, which we just talked about previously. The transitive property. And you can kind of see here that we know that SX goes to XY, and then XY goes to YZ, so we could get rid of the middleman and just put SX congruent to YZ. And that's transitive property congruence. Okay? Not like before where it was transitive property of equality. Now it's transitive property of congruence. So SX is congruent to YZ. But we can also do that again in step 5. We can use transitive property again. Because now we have our SX. There's my SX. Okay? So we know that SX equals YZ. So we got that in step 4. SX equals YZ. And from step 2, we know that YZ equals ZF. So now I can say that SX equals ZF. I'm getting rid of the middleman again. So at this point, it would probably be helpful to us to do what we did in the previous proof, which is to say which steps we're talking about. Okay? So I'm going to go back and do that for you just in case you're confused and you want to kind of follow what happened. So for this step 4, we took that SX was congruent to XY from step 2, and that XY was congruent to YZ from step 3, put them together and got step 4. So I'm going to put steps 2 and 3 over here. And then for the next one, we know that from step 4, that SX goes to YZ from step 4, but also that in step 2, YZ goes to EF. So we're going to put steps 2 and 4 this time for this guy. Okay, then we're pretty much done. Step 5 could be our last step, but it's in the wrong order. Okay, it doesn't say here prove SX congruent to ZF, it's the other direction. So we're going to rewrite that and put ZF first. And I just really wrote that really badly. Let me just try that again. ZF congruent to SX, like that. Okay? And basically all I did is reverse the order there, and that is basically the symmetric property that we just saw earlier. Symmetric property congruence. All right, and that is basically how you would complete this proof. And so now I'm going to have you guys try one over here. Again, I just want to remind you that if you actually look on page 147, you will see an actual diagram that has like a man cutting wood and whatnot. But at the end of the day, there are basically 4 segments that are all kind of congruent to each other, and they want you to prove that. So just wanted you to be aware that this is the part of the diagram that you actually need. You don't actually have to draw the man and whatnot, but anyway, again, if you want to look at the actual diagram, it's in the book on page 146. So good luck with that, and when you're done with that, you will have completed your notes for this lesson. I'll see you in class, and thank you for watching.